students. All right, ladies and gentlemen, we are here for a short segment in our notes regarding a gaseous topic within our phases of matter, and it has to do with our gas laws. We're going to talk about two gas laws that have a lot to do with our phases of matter topic, but this is a brief little segment. Gas laws are laws that describe the behavior of gases under certain conditions. Now, we've talked about solids, liquids, and gases already. And gases, as you know, don't have a definite volume and they don't have a definite shape. These things can change. And because they can change, gases tend to be a little bit more dynamic, and they change under different circumstances. So we're going to go over these two gas laws that help to explain what are some of these conditions or circumstances that allow gases to be, well, quite dynamic. So let's begin with the first one. The first one is called Boyles Law. Now, notice the spelling. It's not B-O-I-L, not that kind of Boyle. This is actually named after Robert Boyle. Should sound familiar to you. And Boyle's Law, and it was Robert Boyle who came up with this law, states that pressure and volume are inversely related. Inversely. That's a math term. Maybe you remember learning about the word inverse or inversely in math class. Basically, what it means is when one goes up, the other goes down. And what exactly am I talking about? Well, pressure and volume. As pressure goes up, volume goes down, and as volume goes up, pressure goes down. They are inversely related to one another. Maybe you can think about it in these terms. Think about blowing up a bicycle tire with a pump, with a hand pump. When you push down on a bicycle pump, what is happening to the volume of air inside that cylinder of your bicycle pump? The volume is decreasing. The volume is getting smaller. But if you've ever pumped up a bicycle tire, you know that the farther down you get, does it become easier or harder to pump that tire up? It gets harder. Why? Because the pressure is increasing. As volume goes down, pressure goes up. That's what an inverse relationship is all about. So Boyle's law states pressure and volume are inversely related. And I have a little video clip here to share with you. And as we are watching this little video clip, I want you to think about the relationship, the inverse relationship between pressure and volume. So check it out.
In a demonstration of Boyle's law, we'll place a balloon in a vacuum bell jar. We'll apply a vacuum which basically pumps out the air in the bell jar. The pressure outside the balloon will be greater than the pressure inside. The balloon expands to try and equalize the pressure. Volume and pressure are inversely related to each other. When we release the vacuum, the pressure increases and the volume decreases. As another demonstration of Boyle's law, we will put a marshmallow peep into our vacuum jar. The marshmallow contains air trapped in a mixture of gelatin and sugar. As we apply the vacuum, the pressure outside is lower than the pressure inside. The air in the peep will expand to try and equalize the pressure. When we release the vacuum, the pressure increases and the volume decreases. As another illustration of Boyle's law, we will put some shaving cream into our vacuum jar. The shaving cream contains air trapped in a soap mixture. As we apply a vacuum, the pressure outside is lower than the pressure inside. The shaving cream will expand to try and equalize the pressure. As you decrease the pressure, the volume increases.
So did you catch that? The inverse relationship between pressure and volume. By the way, this is a vacuum chamber, and what he was doing was sucking the air out or putting more air in to create a vacuum. The balloon was not attached to the tube at all. It was just responding to the air pressure or lack of air pressure inside the vacuum jar here. By the way, there's one reason why they don't inflate weather balloons all the way up on the ground level before they send them up into the air. Because if they did, well, think about it. As a weather balloon travels higher and higher in the atmosphere, the air pressure higher up decreases. So if the air pressure around the balloon decreases, what would happen to the volume of that weather balloon? I won't tell you the answer, but think about that. All right, second law is Charles' law, again named after a scientist. Charles' law states that temperature and volume are directly related to one another. As one goes up, the other goes up. As one goes down, the other goes down. Let me give you another analogy with a bicycle. Perhaps you've ridden your bike all summer long and the winter season is upon us, so you store it in the garage, forgotten about until the next spring. Now, assuming there are no holes in your bike tire, when you're ready to ride the next spring, when it starts getting warm again, you take your bike out and you may notice that your tires are flat. Well, why might that be? Well, think about it in the context of Charles' law. Temperature and volume are directly related to one another. So all winter long, the temperature has declined, it has gone down. What do you think normally happens to the volume of your bike tire? It also will go down because there's a direct relationship between temperature and volume of gases. And to illustrate this, I've got another little clip here for you, which I think you'll find interesting. So let's check this one out now.
So as we've already talked about Charles' law, it states that there is a direct relationship between volume and temperature of a gas. So what we want to do is we want to show this direct relationship by decreasing the temperature of the gas.
Maybe difficult to hear. So he's got a balloon.
Liquid nitrogen.
And he's got some liquid nitrogen, which is really, really, really cold. And he's going to pour some liquid nitrogen, lowering the temperature around the balloon, and let's see what happens. So the temperature is decreasing. Look at the volume of the balloon. The volume is decreasing as well.
As you can see, the volume of the gas in the balloon decreased when temperature was also decreased. As the temperature of the balloon starts to increase back to its normal,
as the temperature begins to increase, notice the volume of the balloon also increasing. So again, a direct relationship between the volume and the temperature, and balloons just create good examples of that. So putting this in mathematical terms, and you don't have to worry about this for the quiz today, but those of you that go on to high school and take high school science, you'll definitely be using these equations, absolutely. But here is the first, let me come over here, there we go. Here is the first gas law. You can see that pressure and volume, this shows an inverse relationship. As volume increases, pressure decreases, and conversely, it is true as well. This arrow simply represents a relationship between the left side and the right side. So this is showing an inverse relationship. Which gas law is this illustrating? Very good. Boyles Law. The second relationship here is illustrating that temperature and volume are directly related to one another. As temperature goes up, volume goes up. As volume goes down, temperature goes down. Which gas law is this illustrating? Excellent. Charles' law. Now, both of these laws can be related together in a famous gas law equation here, which ties together pressure, volume, and temperature of gases under two different conditions, which is what the subscripts of 1 and 2 represent. Unless you're in algebra, we're not going to be going through these equations, so you really don't have to worry about them too much. But if you do plan on going into high school science, which I know you very well may, having these written down, not a bad idea. You can refer back to them in the future and think back to Boyle's Law and Charles' Law as we went over them today. So that's all I have for you right now regarding the gas laws. And next, we'll get started with our lab activities. So until next time, bye-bye.